Imagine an engine that doesn't burn fuel the way a conventional rocket does. Instead, it uses the immense heat of a nuclear reactor to transform ordinary hydrogen into an extraordinarily fast-moving exhaust stream. This is the basic idea behind nuclear thermal propulsion, and it could fundamentally change how quickly humans can travel through the solar system. The physics begins inside the reactor core. Liquid hydrogen is pumped through channels surrounded by extremely hot nuclear fuel. As atoms in the reactor undergo fission, they release enormous amounts of energy as heat. That heat is transferred directly into the hydrogen, rapidly raising its temperature before the gas is forced through a rocket nozzle. The result is simple but powerful. The hydrogen leaves the engine at far higher exhaust velocities than the exhaust produced by conventional chemical propulsion. Chemical rockets depend on combustion between fuel and oxidizer. That means a huge portion of the spacecraft's launch mass must be carried simply to make the reaction possible. Nuclear thermal propulsion changes the equation. The reactor provides the energy, while hydrogen serves primarily as the propellant. That distinction matters because rocket performance is dominated by one brutal problem. Every kilogram of fuel has to accelerate every other kilogram of spacecraft. Nuclear thermal engines can potentially deliver roughly twice the specific impulse of the best chemical propulsion systems. In practical terms, that means significantly more velocity can be extracted from every kilogram of propellant. And the technology is no longer limited to the concepts of the 20th century. Modern reactor development has brought renewed attention to high-assay low-enriched uranium, or HALEU. These fuels contain a higher concentration of uranium-235 than conventional low-enriched uranium while remaining below the enrichment levels associated with highly enriched uranium. For advanced reactor designs, that additional fuel density can enable more compact and capable systems. For space propulsion, compactness is critical. A reactor designed for a spacecraft cannot simply be the size of a terrestrial power plant. It has to survive launch, operate in vacuum, handle extreme temperatures, and deliver enormous amounts of thermal energy while keeping mass under control. Inside a nuclear thermal rocket, the reactor becomes the heart of the propulsion system. Fission releases heat. The hydrogen absorbs that heat. The hot hydrogen expands through the nozzle. And that expanding gas produces thrust. There is no need for atmospheric oxygen because the entire energy source comes from the reactor. The engine can therefore operate in the vacuum of space exactly where conventional combustion engines would otherwise face limitations. But the real advantage appears when the spacecraft begins accelerating. Every increase in exhaust velocity can dramatically improve the amount of mission velocity a spacecraft can achieve for a given propellant mass. That can mean shorter burns, greater maneuvering capability, and potentially faster journeys between Earth and Mars. A chemical rocket can deliver enormous thrust, which is why it remains extremely effective for launching spacecraft from Earth. But once a spacecraft reaches orbit, the equation changes. The ability to efficiently convert propellant into velocity becomes increasingly important. That is where nuclear thermal propulsion becomes especially interesting. A future architecture could potentially use conventional chemical propulsion to escape Earth's surface and then activate a nuclear thermal engine once safely in space. Instead of carrying enormous quantities of chemical propellant for the entire interplanetary journey, the spacecraft could use the reactor to repeatedly accelerate hydrogen to extreme velocities. The objective isn't simply to build a faster rocket. It is to break the vicious cycle of rocket mass. Less propellant required means more mass available for scientific equipment, shielding, life support systems, cargo, or additional propellant. More available performance can enable higher energy trajectories. And higher energy trajectories can potentially reduce the time humans spend crossing the dangerous environment between Earth and Mars. There is still a major engineering challenge. The reactor must operate at temperatures high enough to maximize performance without destroying the fuel, structural materials, or hydrogen flow channels. The spacecraft also needs reliable control systems, radiation protection, thermal management, and a way to safely handle the reactor during launch and operation. So this is not a technology where one breakthrough suddenly makes interplanetary travel effortless. But the underlying physics is remarkably straightforward. Take the extraordinary energy density of nuclear fission. Transfer that energy into lightweight hydrogen. Accelerate that hydrogen through a carefully designed nozzle. And use the resulting high exhaust velocity to generate far more useful spacecraft velocity from every kilogram of propellant. For decades, reaching Mars in a practical timeframe has been constrained by one fundamental problem. Rockets are forced to carry the very mass they need to accelerate. Nuclear thermal propulsion attacks that problem at its source. Instead of asking how much chemical fuel we can carry, it asks a much more powerful question. How efficiently can we turn nuclear energy into motion? If engineers can answer that question reliably, the trip to Mars may stop looking like a multi-year logistical nightmare and start looking like the first major destination in a much faster era of human spaceflight. But there is another side to nuclear thermal propulsion that makes the technology even more fascinating. Getting hydrogen incredibly hot is only half the problem. The real challenge is controlling what happens next. Inside the reactor, temperatures can become extreme. The hydrogen has to absorb enormous amounts of thermal energy without damaging the reactor materials surrounding it. Every component is being pushed toward the limits of what modern engineering can tolerate. And this is where material science becomes just as important as nuclear physics. The reactor fuel has to survive intense heat, radiation, vibration, and rapid changes in operating conditions. The channels carrying hydrogen must remain stable while exposed to temperatures that would destroy ordinary materials. Engineers therefore have to design the reactor as a carefully balanced system. Too little heat, and the hydrogen doesn't reach a sufficiently high exhaust velocity. Too much heat, and the reactor components can begin to degrade. The goal is to find the narrow operating window where the engine produces maximum performance while remaining stable and controllable. This becomes especially important because hydrogen behaves very differently at extreme temperatures. As liquid hydrogen enters the engine, it begins at cryogenic temperatures. It then moves through the reactor and absorbs heat at an astonishing rate. Eventually, the liquid becomes a high-temperature gas. That gas expands dramatically. And when the expanding hydrogen is directed through a converging-diverging rocket nozzle, thermal energy is converted into kinetic energy. In other words, the reactor creates the heat, but the nozzle turns that heat into motion. This is the same fundamental principle behind conventional rockets, but the source of the energy is completely different. A chemical rocket gets its energy from molecular reactions. A nuclear thermal rocket gets its energy from atomic nuclei. That difference gives nuclear propulsion its extraordinary energy density. But higher efficiency doesn't automatically mean unlimited acceleration. There is an important trade-off. A nuclear thermal engine can produce much higher exhaust velocity than a conventional chemical engine, but its thrust depends on the amount of hydrogen flowing through the reactor and the power available from that reactor. For a spacecraft departing Earth's surface, enormous thrust is required. That's why one of the most realistic concepts is not to replace chemical rockets completely, but to use different propulsion systems for different phases of the mission. A powerful chemical rocket could launch the spacecraft into orbit. Once safely away from Earth, the nuclear thermal engine could take over. Now the spacecraft is no longer fighting through Earth's dense atmosphere or trying to escape the deepest part of Earth's gravity well. It can use the nuclear engine where high efficiency becomes more valuable. And this changes the architecture of a Mars mission. Instead of burning huge quantities of chemical propellant throughout the entire journey, the spacecraft could perform powerful nuclear burns to reshape its trajectory. The engine could accelerate the spacecraft away from Earth, coast through interplanetary space, and potentially perform additional burns when approaching Mars.